Google's search index contains over 100 million gigabytes of data. Finding the right information requires more than just keywords. Here's what 90% of engineers get wrong when designing Retrieval Augmented Generation, or RAG, systems. The secret is in understanding the nuances of retrieval, chunking, and re-ranking. By the end of this video, you'll know exactly how to build a RAG pipeline that delivers relevant results with minimal latency. Remember this 100 million gigabytes figure. We'll see why it matters when we discuss scaling. We'll also see how evaluation metrics like recall at K help us measure success.
Let's define the scope. Functionally, we need to retrieve relevant documents based on a user query, augment the query with the retrieved context, and generate a response. Non-functional requirements include low latency, under 200 milliseconds, high accuracy, relevant results, and scalability to handle 10,000 queries per second. A clarifying question: are we dealing with structured or unstructured data? Let's assume unstructured text documents for this design. We also need to consider the context window limitations of the LLM, typically around 4096 tokens for models like GPT 3.5, and how to optimize for cost, because inference costs can quickly add up at scale. We can reduce costs by using smaller models or optimizing prompts.
Let's estimate capacity. 10,000 QPS translates to 864 million queries per day. Assuming each query retrieves 10 documents and each document is 10 KB, that's 864 million times 10 times 10 KB equals 86.4 terabytes of data transferred daily. Storage: if we have 10 million documents, each 10 KB, that's 100 gigabytes of raw data. We'll need additional storage for embeddings and indexes, roughly doubling the storage requirement to 200 gigabytes. Each embedding vector will be 768 dimensions using sentence transformer. So that's 10M times 768 times 4 bytes equals 30 gigabytes for embeddings. This estimation helps us understand the infrastructure requirements and potential bottlenecks.
Now, for the high-level design, here's where most engineers make a critical mistake. They treat RAG as a monolithic process. Instead, we'll separate the read and write paths. The write path handles data ingestion and indexing, while the read path focuses on query retrieval and response generation. This allows us to optimize each path independently for performance and scalability. We use Kafka as a message queue between the write and read paths to decouple the components and ensure fault tolerance because it provides at least once delivery guarantees. SQS was considered, but Kafka's ordering capabilities are crucial for maintaining data consistency. We'll also integrate an LLM for response generation using OpenAI's API. The API endpoint for submitting documents will be post/API/v1/documents text/string metadata/JSON returns document ID/UUID. The API endpoint for querying will be get/API/v1/query query/string returns results/JSON.
Let's dive into the core logic. We'll use a combination of retrieval, chunking, and re-ranking. For retrieval, we'll employ approximate nearest neighbor search using FACE because it provides a good balance between speed and accuracy. FACE uses inverted file indexing and product quantization to efficiently search high-dimensional vectors. Now, at this point, your interviewer will push back. Why not just use exact nearest neighbor search? The reason is that exact search becomes prohibitively slow with large datasets. For chunking, we'll use semantic chunking, splitting documents based on sentence boundaries and overlapping chunks to preserve context. A common candidate mistake is to use fixed-size chunking, which can break semantic boundaries and reduce retrieval accuracy. We use a sliding window of 3 sentences with 1 sentence overlap. Finally, for re-ranking, we'll use a cross-encoder battle like BERT to re-rank the top K retrieved documents based on semantic similarity to the query. We gain higher accuracy, but sacrifice latency compared to simpler methods like cosine similarity. The trade-off is that BERT re-ranking adds about 50 milliseconds latency. We can use sentence transformers to generate embeddings. A potential failure scenario is that the BERT model could fail to generalize to unseen data, leading to poor re-ranking performance.
Let's design the data model. We'll use a vector database like Pinecone because it's designed for high-dimensional vector storage and fast similarity search. Pinecone uses specialized hardware and indexing techniques to achieve low-latency queries. The schema will include document ID, UUID, chunk ID,
integer, text, string, embedding, vector, created at, timestamp, job ID, UUID for data ingestion pipeline, and parent ID for data lineage tracking. Pause and think, what's missing from this schema? We also need metadata to store document source and other relevant information. We'll use cosine similarity for indexing the embeddings. We can also use other indexing methods like HNSW, Hierarchical Navigable Small World.
Now that we understand the data model, let's talk about scaling. We'll use caching with Redis to reduce latency for frequently accessed documents. We use a cache aside pattern because it's simple to implement and avoids cache stampedes. On a cache miss, we query the vector database and backfill the cache. This keeps our P99 under 50 milliseconds for read-heavy workloads. For the vector database, we'll use sharding to distribute the data across multiple nodes. Remember the 100 million gigabytes of data we mentioned in the hook? To handle that volume, we need horizontal scaling. We'll also use replication for fault tolerance. Finally, we'll use a CDN to cache the generated responses closer to the users, further reducing latency. We might be tempted to use consistent hashing for sharding, but a simpler range-based sharding strategy is sufficient for our use case and easier to implement. This is where most people go wrong. They over-engineer the sharding strategy. An experienced interviewer will probe, what happens at 10x scale? Here's the key. We'll need to reevaluate our sharding strategy and potentially switch to consistent hashing to handle uneven data distribution.
Let's discuss reliability and operations. For fault tolerance, we'll use replication for all critical components, including the vector database, cache, and message queue. We'll also implement circuit breakers to prevent cascading failures. For monitoring, we'll track key metrics such as query latency, retrieval accuracy, and error rates. We'll use Prometheus and Grafana for monitoring and alerting. The data ingestion pipeline will be designed to be idempotent so that we can safely retry failed jobs. We'll also implement data lineage tracking to ensure data quality. We can use tools like Airflow to orchestrate the data ingestion pipeline. We can use evaluation metrics like recall at K and NDCG to measure the quality of the retrieved documents.
To summarize, we've designed a scalable and reliable RAG architecture using retrieval, chunking, and re-ranking techniques. The key trade-off is between accuracy and latency. We chose FACE for retrieval, semantic chunking for context preservation, and BERT for re-ranking. Potential bottlenecks include the re-ranking step and the vector database query latency. Next steps would be to implement A/B testing to evaluate different chunking and re-ranking strategies, and to evaluate the system using metrics like recall at K and NDCG. This is where most people go wrong. They don't continuously evaluate and refine their RAG pipeline.
Get more system design breakdowns, coding patterns, and technical deep dives delivered straight to your feed. Hit subscribe and turn on notifications.